Good morning, students. I hope everybody's doing well. Professor Ron's been a little bit under the weather for the past couple of days. So if I look a little bit scary, I apologize. Uh, I'm from North Carolina originally, and the Texas weather I really like, but when the winds blow in all kinds of funky stuff, allergies and colds and things, I run, and so of course I breathe all of that in. But it's good. Um, I just like I say, take care of yourself. The best thing that I try to do is drink plenty of water and try to get rest. And even if the rest is not that wonderful, where you can actually just lie down and give yourself some stress relief, that's always a positive thing. So take care of yourself. I know I've asked you to do a lot of work. I mean, I'm probably one of the toughest professors you have, but you know, when it's all said and done, you'll have plenty to show for it. Now, what we want to do today is complete some of the work from section 2 and then cover section 3 on the integral test. So all of this stuff is connected, and that's really good because we get to go back and use Cal 1 and even a lot of pre-Cal stuff. So let me go ahead and share my screen. Now here, I've gone ahead and written the statement of the theorem about geometric series. Now remember, back in pre-Cal, and this is probably something that you usually cover at the end of the class, so by then you're so tired, you're like, I don't remember this, Professor Ron. I had a colleague one time, he started pre-Cal with sequences and series, and I said, that's not a very good idea because it's a little bit more complicated than maybe they can stand at the beginning. But I guess everybody has a different way of looking at things. But we've talked about some basic ideas about series, the telescoping series, and basic attributes and characteristics of convergent series that will help us to basically characterize series before we have to do too much additional work. Like the telescoping series, the geometric series is another type of series, which is our friend. Once we understand it, relatively simple to actually analyze. And so let me remind you of this. You may have had similar notation in pre-cal, but if not, it will still work. So we're going to start with two fixed real numbers, A and R. And we will suppose that A and R are non-zero, and normally the R is non-unity, just because multiplication by 1 is the multiplicative identity, and that doesn't move anything forward. So we're going to define the geometric series as the sum, and here's one way to write it, 1 to infinity of A times R to the n minus 1. Now, when you expand this, this is pretty much what we get here. And of course, you can change the index around and start at 0, and then of course change the power here of R to n. You can always re-index a series and make it more user-friendly, and we will do that some in this class. And also, you will do it when you get to differential equations, when you discuss power series solutions. So you're going to always have plenty of algebraic flexibility. So when we expand the geometric series, it has this common form, just like the arithmetic series that you studied in pre-cal. We'll have a first term, which we normally call A. I guess you could use any letter you like. And then you have the nth term, which is this one, A R n to the minus 1. And so what we want to do is characterize, again, the geometric series by these two non-zero real numbers. And we're going to use some ideas that we actually discussed in the last class. So this geometric series will diverge. That is, the sum does not converge to a real number when the absolute value of R, which we call the common ratio, is greater than or equal to 1. That has everything to do with the fact about that limit R to the n that we discussed. But you can look at this and say, well, I bet it will converge here because the limit of r to the n will exist. We know it's 0. So if r in absolute value is less than 1, that is between -1 and 1, exclusive, then the geometric series converges, and the sum is a over 1 minus r. The geometric series is like the Pythagorean theorem. It is so ubiquitous in mathematics and science that we would struggle to do our work without it. When you take complex variables, you'll scratch your head many times thinking, you know, what would I do without the geometric series? It's such an important component of mathematics. And I probably would say that if you've had some science classes with physics, you have seen this before at play. So it's a wonderful object to study. Now, what we want to do is talk a little bit about why this is true and then do some examples. Now, what we want to start with is to look at the partial sum. So, like I said before, we construct a sequence of partial sums to figure out whether or not the infinite series converges. So let's go ahead and do that and just do some simple algebra. And you may, again, what I'm doing now, you probably have seen before, but it's good to review it. So we'll start here, but we'll change to k. K equals 1 to n, a, r to the n minus 1. Now, what we want to do is perform some algebra here. We've got this nice formula here, and what we're going to see, just like we saw last class, is that we can create a telescoping sum. So now what we do is we consider the following algebraic expression. So we're going to take s sub n, and we're going to subtract r times s sub n. So we're going to take this partial sum, and we're going to take the difference between the partial sum and the partial sum multiplied by r. Now, of course, we can go ahead and factor the s sub n, and this will leave us a 1 minus r. Now, when we think about this, this is an algebraic expression for this, but now let's go ahead and write what we get with both of these in this particular case. What does this give us? So we'll now focus on this. So let's just go ahead and be court reporters. So this will just be that, k equals 1. It's good to be able to manipulate the series. And so that's what I want to give you practice in doing, just like you did in pre-cal. And then, of course, this is a finite sum. You can always use algebra on series. You can run constants and numbers inside and multiply with no problem. If it doesn't converge, it's just not very useful. So we have k equals 1 to n. And then if we multiply by r, we add 1 here and we get an additional copy of r. Now, when you look at this and you think, okay, and you're all probably looking at me and saying, Professor Ron, these are k's, forgive me. That's the index variable. So let me make those into k's. So the index variable is k, and so when we switch, we need to switch these out. So make that change in your notes. Now, when we look at this, we're thinking, okay, we would like to be able to subtract these. That is, maybe kind of put this together in a way that makes more sense to us. Now, what I want to do, and it may or may not be helpful in this case. Look at this particular series where we have k minus 1, and look at this series where we have k. If we want to subtract them, then it would be more advantageous to have the powers equal so we can perform some algebra. So let me show you a little trick that will be useful in this class and later classes. We want to change the index here to k, that is the power. So we're going to make it bigger, so we have to make this smaller. So bigger by 1, smaller by 1. just a little bit of series algebra. Oh, and then of course we're making this smaller, so we've got to make that smaller, adjust throughout, so to speak. So this one stays the same. So let's just see what we have here. Notice now the powers or the generating terms of each of these series or finite series is the same. So just like I said here, we did a replacement. We replaced the k minus 1 with k. So we added 1. So we need to adjust the index by subtracting 1. So now notice when k is equal to 1, we get an A. When k is equal to 0 here, we also get an A because r to the 0 by definition is 1. So that was just an index adjustment, okay? And I'm doing this, I wasn't planning to do this, but I thought, you know, why not go ahead and write this way so that you can see the actual algebra going on. So now let's just do a little comparison here. Notice this has the k equals 0 term. And then of course, this is a 1 here. The math is self-correcting. It's amazing when you do these series things. This doesn't work in English. If you spell something wrong, it probably stays wrong because you don't really go back to it unless you repeat the word. So now when you look at this, you're thinking, okay, we have a k equals 0 term. So we're going to write that. The k equals 0 term is A. And so now we can write plus k equal 1 to n minus 1, a r to the k. So that's write this down. This is the k equals 0 term right here. And then of course, over here, we have a k equal n term that we don't have here. And when we actually write that down, that's a to the rn. So now we have minus k equals 1 to n minus 1 minus the k equal n term. So we have k equals n. Now, the whole idea behind this, I mean, I could wave my hands over this and say it's obvious, but that's not very good because what makes you an excellent math student or more mathematical is that you can actually write it out. So now we see that these terms, and of course, let me go ahead and write the generating index. These two objects are equal and opposite. They absorb. That's the telescoping part. So now I wasn't lying to you. And of course, let me put in the minus here. So this is the telescoping part. This absorbs. So like I said, this is telescoping. That's the term we use when then basically all of the terms absorb. Even in the infinite case, we're going to see that today. So now you're thinking, okay, well, that's really nice. This geometric series is really like the series we studied last class. So now the only thing that's left is A minus ARN. So we have the first term and the nth term, but again, you know, Professor Ron just factors everything to death. We get A 1 minus R to the n. So now this is nice and reduced equals this. So equivalently, if we solve, and again, here we're tacitly assuming that R does not equal 1, and obviously it has to be the case. R equal 1 would not be a very interesting series. It'd just be the constant series. A, and we're adding up all the A's. So the sequence would be A. So we're not really interested in that. So we get the partial sum, the nth partial sum will now be A times 1 minus R to the n divided by 1 minus R. So that gives us an expression for the nth partial sum. And now you can see where the limiting process takes over. So with this partial sum, we want, eventually what we want is for the n to pass to infinity. And so now we can finish this off. We can just say when the absolute value of R is greater than or equal to 1, the limit as n approaches infinity of R to the n does not exist. It either we get alternating or we get infinity or whatever, it doesn't exist. And you can show that. We did the case when R was less than 1 or between 0 and 1. And then when R in absolute value is less than 1, we know the limit is actually 0. So when we pass to the limit here with this term not having a limit, that tanks the whole thing. So then this implies that the limit as n approaches infinity of S sub n equals the limit as n tends to infinity of A 1 minus R to the n over 1 minus R. And then of course, all of this, the A over the 1 minus R, you know, that's just a constant which we can extract. And then we're just left with the limit as n approaches infinity of 1 minus R to the n. And of course, that limit's just 1 because that's 0. So that just gives us A over 1 minus R times 1, which is A over 1 minus R, which of course is the infinite series. And I'll just go ahead and write what I've written up here. So I wanted to go through this because this is really a pre-calculus exercise, even though most pre-calculus students could not do this unless you had me for the class. The thing is that this kind of manipulation, even though it's just basic arithmetic, is not the kind of manipulation you normally do unless your professor just makes you do it. And so the idea here is that regardless of this knowledge or whatever, you can still see that we have a very nice recipe for the geometric series. They're easy to spot. And plus, once we figure out what the R is, then all we have to do is check to see that this is satisfied. If it's not, then we're done. So this basically gives us a way to analyze series that most series do not provide. We will have other convergence tests that will be very user-friendly, but when it comes to telescoping and also the geometric, I guess we could basically characterize them as the same type of series, or at least they have similar attributes. The telescoping effect is tantamount to getting this formula for the partial sum. So like I said before, in general, finding a actual sum of the series, it is difficult and requires maybe more mathematics than we can do at the time. However, that's never an issue. If you're working on an engineering project and you only need a sum good to 3 or 4 decimal places, series sums can be approximated. And so that can actually serve as a intermediary to do the calculations. So again, remember here that this involves everything that we did last class, and then here we just have a little bit of practice with the algebra of series. And so again, as you make these adjustments, they're not really rules, they're just basic common sense. I mean, if we want to combine series in an algebraic way, their generating sequences must be equal, in the sense that we must, for instance, either we have a situation, not equal, either we have a situation where we've gotten rid of extra terms so we can put things together and then we can actually factor. We just got really lucky here that both of these generating sequences were actually equal. So the idea is when we want to combine series, and this is actually turning out to be a power series, which we'll study later, we will use that type of technique. So again, there are all kinds of checks that work their way into these types of calculations that as you move through, you can always simply make adjustments as necessary. Like I say, the only sad thing is that when we do the nth partial sum, we're forced to change the index just for sanity reasons. Otherwise, it would be very difficult to manipulate things. So let's look at a couple of examples of this. Now, there are cases where you might see an example of a geometric series in another section that's covering another test. And so you might say, well, I'm just going to use the geometric as opposed to this new test, or maybe you'll just practice the new test. You always have the flexibility. It's kind of like an integral. It's like, well, I've got an integral table here. You know, I print out my integral table. And so I can use my integral table if I need to. The idea is that we utilize techniques that push the problems forward in a way that gets us to the finish line, hopefully in an efficient manner and a correct manner. So the first thing I want to do is utilize the geometric series to actually write a repeating decimal as a fraction. So here's what I'll say: use, and of course there are other tricks to doing this problem, but we want to practice the geometric, and I'm sure you might even know about it. Use the geometric series. Use the geometric series to write the repeating decimal. Notice we can always write a repeating decimal as a fraction. The non-repeating are transcendental, and that's not possible. So to write the repeating decimal as a ratio of two integers. I used to show my students another way to do this, but I felt bad about it because it wasn't giving them any practice utilizing the geometric series. So I thought to myself, you know, I need to help my students move forward. But of course, on a test, I'm sure they were glad to know shortcuts, but we want to practice the geometric. So here's the actual decimal. We have 0.0 or 0.215. So the 15 is the repeating part. So 0.2151515, etc. So first, what we want to do is notice that this is basically, this part here, the repeating part, is geometric. And so that's what we want to express to use our sum formula. So let's do that. So this will be 0.2 plus, and now we'll have 0.015 repeating. Now, of course, 0.2 is 1/5, 2/10. And then now what we can do is go ahead and write this as a geometric progression. So we'll get 0.015 and then 0.00015 I won't write out too many of these. You see the idea, and then 5 zeros, etc. So when you've got a repeating decimal, you just take the repeating part and then move it, transition it down. So here we have the 15015, then we have the 0.00015, and then of course we string of 5 zeros and then another 15. So basically what you're seeing here, as we go from here to here, what are we doing? I mean, what is the process here? Notice we're adding 2 more zeros. So this is applying that R is 1 over 100. So R equals 1 over 100. And if you like, the first term here is this dude right here. So we'll just say A is 0.015, which is 15 over 1,000. So we're just characterizing this as a geometric progression. Now, this will be 1/5. So plus, now one thing that I want to do that will make this a little bit easier, and I'll give you another way to actually write this that will be convenient here. Let's go ahead and factor for instance, here, when we think about what we have here, well, let me just do it this way. Let me just go ahead and do it, since I'm already writing all this out, let me do it this way. So I was going to show you another factoring technique, but we just did this. So notice if we have this here, let's see, where are we? Oh yeah. If we got, let's go back to the theorem. If we have the A and the R, then we have this formula here. So let's go ahead and use it. No need to do any additional factoring. So now by theorem, I'll just say theorem 9.6. Now A is just 15 over 1,000. And then 1 minus R is 1 minus 1 over 100. So what I was going to do, ladies and gentlemen, is show you some additional factoring techniques. But what I went ahead and did here was just go ahead and write down all the particulars, the A and the R. And once we have that, we can go directly to the theorem, which is A over 1 minus R. So that'll save you some time. So maybe this isn't as long-winded as I might have said initially. So we have 1/5. Students are always surprised when I have stacks of notes and then I prove something completely different, because at the time something else comes to my brain and they're like, that scares us, Professor Ron. I said, no, that shouldn't scare you. That should make you feel good that I actually know what I'm doing. So we have 99 over 100. So this will just be 100 over 100 minus 1 over 100, which is 99 over 100. And then of course we have 15 over 1,000. So we have 1/5 plus, we'll wait to reduce all of this because we've got some nice numbers. So we've got 1,000. And then of course 100 over 99. So 1/5. So now of course here, the 100 absorbs and we just have a 10 here. Good old eraser tape. So now we have a 1/5. And then here we can choose, we can just go ahead and divide by 5 first and get 3 over 2 times 1 over 99. And then of course divide by 3, so this will be a 1/2 times 1 over 33. So we have 1/5 plus, well, 2 times 33 is 66. So relatively prime, I think you might say between 5 and 66. So this will be what, 5 times 66. So this will be 66 plus 5. So that'll give us a 0 and then a 3. So 330. And then, of course, 71. So when we look at problems like this, like I say, the most time you're going to spend is just doing the arithmetic here. But like I said before, when you prove a result, every time as a mathematician, every time I actually write up notes or I prove something, I've done other research. And so I'm going to look at something differently. And so I'll write it and say, well, let's do it this way. I mean, because something in your brain will click because you move things to different levels and you're thinking, well, let's just go ahead and use the theorem. We just proved it. So why not do it this way? Often what we're going to do when we do a problem is that we remember a technique that we used before. And if you haven't worked with the theory any, then that will be the technique that's on your brain. So as you become STEM professionals, some of you will become, well, not math professors, but maybe engineers or computer science people. You will develop techniques over and over and over and over. So someone will come up to you when you start, and then 5 years later, another person will come with the same question, and your answer will be completely different. The result will be the same, but you will have changed the way you look at that particular item. That's what you will do, and that's what you've done with your mathematics, at least even in the short time you all have been doing math. So again, remember that in order to do STEM, you're always doing STEM. You're always doing things and cultivating and improving the knowledge of what you have. So it's not stagnant. It's always evolving. So don't be surprised that sometimes you get a little bit frustrated. It's like, well, why can't I just stick with one way? Your brain won't let you do it. You'll just have to evolve with it. So that's kind of a fun problem. I'm not going to show you another way to do it because I want you to do it this way. And this is short enough to actually affect. And of course, what I was thinking is that, like, if WebAssign asks you to write this in a series, then you can fit in the A and the R and do whatever you need to do and use whatever indexing that they say. If they want to start at a particular index, then you adjust for it, just like we did in our proof. So nothing for free. Nothing is ever free, ladies and gentlemen. The idea is that we're always evolving, especially when it comes to math. Now, here's a trivial example, but let's just look at it. So for instance, it says find all values x for which the given series converges. Of course, this is a loaded question. So for instance, we've got this. So this is really hearkening to the power series that we're going to do later. But I like what WebAssign does. I like what Dr. Larson does. He just kind of throws these in and says, okay, go with it. Now, this is the easiest type of example when they give it to you in the nice, neat form here. Notice we do have a geometric series here. That is, if we look at this and we start to expand it, let's just write out a few terms. I mean, this starts at 1, and then the power is the same as the index, that is n. So we get what? We just get 6x plus 6x squared plus 6x cubed, etc. So sometimes it's just good to kind of get a feel of what the series looks like outside of the more compact form. But of course, we've already seen how operating on the series in this form is much more clean and efficient as long as we keep track of indices and powers. And so if we wanted to figure out the values of x for which it converges, we can go back to the theorem. So now what we note is we observe A and R are the same, namely 6x. So we can just, I'll write down A just for extra, is 6x, and R is equal to 6x. So for convergence, so this is where we're glad when we have a geometric series. For convergence, we need R 6x in absolute value less than 1. And that describes all the values of x for which this will converge. And so clearly, this is just a nice little, a conjunction, right? So this will be what, 6 times the absolute value of x less than 1, using properties of the absolute value. So the absolute value of x is less than 1/6. And this is just a conjunction that was beaten into your head in pre-cal and calculus 1. So x will live between -1/6 and 1/6. So when we do power series and we do intervals of convergence, we'll be doing a lot of computations like this. So this is kind of a preview of what we will be doing when we get to those items, and you will enjoy that. There'll be some things in this chapter like this that are really fun, nice arithmetic problems that give you a little breather from the U and the DU, which probably you're getting a little bit winded up. So now the next example, or the next part of it, was to say, well, then what's the sum? Compute the sum. Well, again, we just use the theorem. We don't have anything to do, but we've got that beautiful theorem that we proved. So then we say n equals 1 to infinity of 6x to the n will just be a over 1 minus r. So that's 6x over 1 minus 6x. So remember, as we've used up here, we can rewrite this many ways. We can say n equals 1 to infinity ar n minus 1. We can start at 0, which is often very popular. I use this for the theorem, made my life more difficult, but I thought maybe that's what you used in pre-cal, and I use that in pre-cal, so I used it. And then, of course, if we make this smaller by 1, we make this larger by 1, just, basically compensation like we do with coefficients in the integration process. And of course, this is just a over 1 minus r. So we keep using this result. And here's another application of it. So when you're working with power series, within the interval of convergence, the power series will represent a function. So we will treat it like a function, and it'll have all the nice properties that functions have. So moving to the next level and starting to understand how your calculator works requires that we understand infinite series and power series. So it's one of these things where every time you use that Google calculator or that fancy calculator that you have, that's calculus at work. So we might have the technological aspects to make computers and cell phones and such, but the logic and the arithmetic had to be invented first to make them actually power. So it's amazing how we evolved, and the math will never leave us. We'll always have to know how to do math. Okay, so let's go ahead and look at a situation where, okay, we've got these geometric series here, and we've talked about basic aspects of series. Let's look at another type of series, which is based upon a function analysis. Now, we like integral tests that aren't too long-winded, but we also like integral tests that are very robust. So if we've got this geometric series, then we have this beautiful result that tells us when it converges, and then it gives us a sum. And like, don't get used to that, but we like that. We like telescoping, even though we might have to do a little bit of arithmetic. The idea, I'm going to do another telescoping example and utilize some logic. Remember that problem we did? We wrote out a bunch of terms to see that they all absorbed. We really didn't need to do that. I mean, you can just look at the form. I'll say, well, look how the denominators differ by 1, and notice that they're always going to absorb. We can make certain observations that don't require us to write forever, just like in the proof of the geometric. But I did a little extra work to show you that the actual series does telescope. Now that took extra work, even though we could have not done it and made some efficient observations to move forward. So what we want to be able to do is hopefully learn new tests. Maybe they're not going to be as great as the geometric test, but at least it'll be something that we can apply and move our understanding forward. And so in this next situation, we have what we call the integral test. So this is in 9.3. And I'm sorry we're back to integrals, but we can't get away from it. This is a very robust test, integral test. So when you look at the integral test, you're thinking, okay, so what do we need if we've got to compute an integral? Well, hopefully whatever we're going to integrate has a Riemann integral. And if we're thinking about an infinite series, we're probably going to have to do an improper integral, because the upper limit would have to tend to infinity if we're letting n tend to infinity. So here's how it goes. This is theorem 9.10. And so we say, suppose that f is positive. We're going to have three conditions here. F is positive, continuous. So basically, we as x approaches c in the limit of f of x, we can replace that with f of c, so we don't have any holes in the function. Continuous and decreasing. So you're thinking, oh, either some algebra or some calculus for decreasing, or x greater than or equal to 1. Now, of course, maybe we can't really get 1, maybe it's 2, maybe it's 3. So basically, this has to work eventually. So if the actual problem, starts with x equal 2 and greater or whatever, that's no issue. That's not going to cause us any problems. So that's why I say eventually. And then what we want to do is define the generating sequence. The generating sequence, and this won't be a surprise, will just be f of n. So we've got this nice function that has all these characteristics. It's positive, it's continuous and decreasing on this interval. And so we define a generating sequence for a series to be basically, as we've done before, evaluating f at positive integers. So we're restricting the domain. Then the series n equals 1 to infinity of a sub n converges if and only if. And this is why I said it was robust, because it moves in both directions, but we really only focus on one side. If and only if the improper integral f of x dx, as x runs from 1 to infinity, that is, converges. So the nice thing, maybe one thing students will say, well, I'm going to try to use anything but this. I don't want to have to compute the improper integral, or that's going to take longer or whatever. Sometimes that's the case. Sometimes we can use other tests. but this is a very robust test, and it gives us a nice way to approximate a series with the improper integral to decimal places that we may desire. So this test I will call robust. It gives us lots of good information, and it's an if and only if. So this is the kind of test that we like. It reminds us a little bit of the geometric series test. So when we look at this, this is somewhat important. Let's just go ahead and think of why this works. I don't often do I don't justify everything, but the ones that are really important that give you understanding, we need to do. So what we're going to do is look at this direction because it's the hard one, but it's simple to do. So we're going to assume that this is true. So we're going to suppose that the integral from 1 to infinity of f of x dx actually does converge. So we're going to say this equals L, which is a real number. And what we want to do is partition an interval from 1 to n. So we're going to fix n element of the natural numbers, and I will state this such that n is bigger than 1. So we don't want to, we don't want to just go 1 to 1. There's nothing there. So, some n bigger than 1. And partition, just like we did in calculus 1, partition the interval from 1 to n by one of the most user-friendly partitions in the world, the natural numbers. So we do 1. Don't you wish this were always the case? Never before. We often have lots of unfortunate arithmetic in calculus 1. So 1, 2, 3, 4 up to n. Now what we want to do is write an upper sum. This is how I've written it in your notes. Write an upper sum using left endpoints because it's decreasing. That'll give us the upper sum, the circumscribed rectangles, left endpoints. And write a lower sum using right endpoints, again, because the curve is decreasing. So what we want to do is notice the subintervals are all of length 1. So this creates a very simplistic sum. Note that the delta x sub I for all I is just 1. The difference between each of these partition elements is 1 for all I. So that's a basic simplification that we like. So now this implies, so the delta x sub I, nothing to work with, just 1. So the upper sum, again, we're going to use the left endpoints. This will just be the sum. That is, we're thinking with the left endpoints, so we're going to have f of 1 times 1 and just move over to f of n minus 1. So this will be f of 1 times the 1. That's the area of the triangle, but it's of the subinterval, or the length of the subinterval. So we just times 1, but we'll leave it off, plus f2. And then, of course, as we get to the number right before here, I'll just squeeze it in. N minus 1. So when we get to the last subinterval, the last evaluation at the left endpoint will just be plus f of n minus 1, because we're using left endpoints. And remember, with the decreasing function, the left endpoints are the larger value of f on that interval because of decreasing. So this hypothesis is very important. None of this would work otherwise. So now this is just if we think about the fact that we've made this definition here, that's just a partial sum. So let's write this as a partial sum with our summation notation. And Professor Ron will use a K this time and not whatever, n minus 1. And I'll be sure to use a K here. So what we see is that this is just the partial sum where we add the first n minus 1 terms of our sequence. So there we go. So very simple because of the way we've set this up. Again, math, remember in Calculus 1, you have to find a partition, okay? So the beauty is that the theory of the Riemann integral is very flexible, and that's really what confounds everybody. You know, when you prove that the sum of Riemann integrable functions is again Riemann integrable, again, you have to use the partition, and you have to actually push the arithmetic forward in a way that gets you to a sum that actually converges. So again, the idea is we did sums back in Calculus 1, but it was with the partition going to 0. So it's a very different kind of object. Even though it's still an infinite sum, it doesn't have the same flavor as these. So similar, but not the same. Now, for the lower sum, we just use the right endpoints. So now we're going to start here and move all the way to n. So we leave out the f of 1. So I put the 2 there so I didn't have to squeeze that in. So now when we do the left endpoints, remember on the decreasing function, those are the smaller values of f. So we start here at the right and move all the way to n. So notice, and this is what we'll do. We'll be creative. This will be the sum, k equals 2 to n of f of k. And then we'll just say, okay, well, we left out the first term, so let's just write that as the nth partial sum minus the first term. So basically, we sum the first n and then take away the f of 1 to get that. So we write these in terms of the partial sum notation. So I mean, cheap is cheap. I mean, this is some cheap arithmetic. It's not difficult, but it is very clever. It is very clever. That's how you develop techniques in mathematics. I learned some of the most clever ideas about math back as an undergraduate. And so like I'm saying before, this will help you think about partitions in the future as you work new engineering problems. So now what does this give us? So we can take these partial sums and get a bound. So the lower sum will be the lower bound. So this implies, and then of course the integral is the exact fit. So that's in the middle, 1 to n. So remember the integral is when the partition goes to 0, so you can't see the difference. There's no error involved. And then the upper deal is this one, s of n minus 1. So when you draw the curve, this is always in between the exact value of the basic area under the curve above the x-axis is always in between a lower sum and an upper sum, always. That's what you learned in Calculus 1. So now, and this of course is for n greater than 1. So this is like, all right, this is a good thing to know. So now by hypothesis, now we're done pretty much. By hypothesis, we have a positive function. So the partial sum, any of the partial sums, is what? Non-decreasing. We're always adding a positive quantity, so there's no way that it can decrease. So it's non-decreasing. And we remember this idea. That is 1 to infinity of f of x dx equals L, which is a real number. Thus, so if we look at this, we can just kind of readjust this. So we can just add the f of 1 to this side, and then we can replace this with the even larger value, which is that. Thus, S of n is less than or equal to, using this end of it, f of 1 plus the improper integral here, which is also an upper bound, L. So what we see here is that the sequence is non-decreasing and bounded above. Hence, S of n is non-decreasing and bounded above. I mean, all we need is an upper bound, and that's even a better upper bound, that guy right there. So by monotone convergence theorem, and we'll just write it this way. S of n, the sequence of partial sums, converges if and only if, right up here, this converges. The infinite series converges. So you're seeing here is that what you can do with these kinds of problems is you can say, well, you know, I can verify the hypotheses, or if I've got kind of an abstract problem, let me just see when the improper interval is going to exist, and then go back and check to see that all these hypotheses work. That usually is a shorter process depending on how complicated the problem is. But now let's look at this. So we've got this part. If we assume this converges, then this converges. Now let's look at the opposite part. So, you know, sheet of paper here. Let's look at the contrapositive. So basically what we want to do is assume, yeah, I'm pointing at something you can't see. We want to assume this and show this, but we're going to be crafty. We're going to do the contrapositive. So we're going to assume the negation of this and show that this is negated. So in the other direction, which is this one, we want to do the contrapositive, just like we did with the divergence test. Contrapositive. So suppose that in this case, the improper integral actually diverges to infinity, that it doesn't converge. Then, and this is where we go back to our inequality. If this diverges to infinity, then so must this, and that's just an nth partial sum. Then the limit as n approaches infinity of s sub n minus 1 is also infinity. Again, by our handy inequality, we just use this end of it. Now this blows up, that's an upper bound, it must also blow up. So that's really a comparison test there. Then if and only if the series diverges. So this was the easy one. So we're done. So remember, the contrapositive is like what we did last time. We say P implies Q is equivalent to not Q implies not P. And this is what we call the contrapositive, and this is often easier to prove. And that's probably something you learned in high school geometry, but if you did, it might be a little bit rusty, but I've already talked about this. This is the contrapositive here. The contrapositive, just to review what we did last time. So what we're seeing with the integral test is that we have a setup that's not half bad. That is, it's probably not too difficult to verify the hypotheses. The continuity part, we use simple continuity rules from theorems from Calculus 1, and then the positive part won't be difficult to do. I mean, it's either positive or it's not. I mean, that will not be hard to show. That'll just be based on the function. And then, of course, the decreasing part might require either some basic observation or a little bit of calculus, a first derivative test, where we have increasing, decreasing, or just the first derivative, basically. So let's look at an example of this. Now, like I said before, ladies and gentlemen, in general, like it's just like doing integrals. Oh, do I have to use this test? Do I have to use this technique or this technique? With series, it's the same way. If I asked you to figure out whether or not a series converges, you can use any test you like. Or I might say, okay, utilize a particular test so you can practice with it. But the idea is it's just like doing integrals. You can utilize whichever test applies and move forward with it. So let's look at a very straightforward example. I mean, we learn something and say, well, we really couldn't do this before, so maybe this is a good example. And then we're going to write down some obvious new rules that we get from the integral test, which we're going to make your life a lot easier. But I want to do this simple example first. So now you're thinking, we kind of, it's like L'Hopital's rule, that we have to basically look at this as a function of x. Well, first, when we look at this, we're thinking, okay, well, this is a positive term series. N equals 1, and we have 2 divided by 3n plus 5. Okay, those are positive terms. And then we're thinking, okay, well, it's not geometric, and of course, no way that it could telescope, so we don't really have anything to work with. So then what we do, we'll just say, and I'm gonna write this out. I'll say prove the series diverges. Prove the series diverges. So you're saying, okay, well, right now I just have the integral test. So we're going to say, okay, let f of x equal 2 divided by 3x plus 5. Or if you want, later on, we can just say 2 times 3x plus 5 to the negative 1. Now, when you look at this, you think, well, you know, we can verify all that other stuff, and we can do it now because this is a simple case. First, it's clearly positive. X is positive. 3x plus, well, just say, just like here. 3x plus 5 is positive for, this is very simple, clearly. And 2 is positive for all x. This implies f of x is clearly positive for x greater than or equal to 1. In many cases, you can just say x is clearly positive. That's like general math right there. But this is using function notation, which you didn't have in general math. And then you say, okay, well, continuous, absolutely continuous. This is just a rational function. It's a ratio of 2 polynomials. It is continuous where it is defined. So f of x is defined on 1 to infinity. This implies f is continuous. That's a theorem from Calculus 1, continuous on 1 to infinity. Rational functions are continuous where they are defined, okay? I know we need a standard version for Cal 1. We need Professor Ron's standard version, and then everybody would be on the right track. Now, then what's the last part? Decreasing. You look at this and say, yeah, this looks like it's decreasing because, well, the denominator is growing and the numerator is fixed. So you could just say f, this is very simple. And the only reason we're doing this is because we only have one object to worry about. If there's more stuff here with a variable outside of the end, then we're going to change the way we look at this. So f prime, we'll just take the derivative here. We get -2 times 3x plus 5 to the -2, which is just write it this way if you like, which is clearly less than 0 for x greater than or equal to 1. Now it's always 0. It's always less than 0 where it's defined, but again, we're just interested in that. I mean, this function's always decreasing. It's always decreasing where it's defined, but we just are interested in that. So you don't have to worry about the fact, well, do I need to be complete? We're just worried about some point on the real line, 1, 2, 3, or whatever, and then off to infinity. So that's all we need. So this means that the integral test is applicable. So we can apply integral test. And so now we just check the improper integral. So now we have the integral from 1 to infinity of f of x, which is 2, 3x plus 5 dx. So now, if you like, you can factor the 2. This is the limit as b approaches infinity of 1 to b. And then, of course, we've got the 3 downstairs, the 3x. So we need 3x plus 5, 3 dx. And then, of course, we have to pay for it with the 1/3 there. So this is easy. I mean, this is simplest integral in the world. And then, of course, improper. So we just let b tend to infinity. So now we have 2/3, the limit, as b approaches infinity. And now, if you will, this will just be the natural log of the absolute value of 3x plus 5, evaluated from 1 to b. So we get 2/3, the limit, as b approaches infinity. So we'll substitute b. So we have natural log 3b plus 5 minus the natural log. And now we put in a 1 here, and that just gives us, 3 plus a 5, which is what? 8. Now notice here, this is just going to get absorbed, so to speak. But what we're looking at here is that the natural logarithm function increases. So this will diverge to infinity. This does not have a limit. So this is infinity minus minus some positive number times 2/3. So this is basically 2/3 times infinity, which is infinity, and therefore diverges. So we have proven that this series diverges. So you're thinking, wow, you can shortchange this a little bit. I just wanted to go through the details. In some cases, it'll be very clear. I mean, lots of times as a practicing mathematician, I will say, well, that clearly diverges by the integral test. What am I thinking of? Is that all of these things you just kind of look at and say, yeah, that's true. And you look at the integral and say, well, that's going to blow up because that's a log function. That's du over u. And so boom, you just say, I know this diverges by the integral test. Well, the first time you do it, you need to work through the cases. And as you get more adept at doing it, then you can see how all of this fits together. But there might be cases where the positive part, you say clear, the continuous part, clear, it's continuous where it's defined, and then maybe computation of a derivative. But notice, we needed this test to prove this. So every time you do a math problem, you're doing a proof, really. You're doing a proof. But with the infinite series, we're saying, okay, we're trying to prove, just like you prove that an equation has a solution basically when you solve it. Here we're saying, okay, we can't apply any test we've learned before because we don't really know many. And the integral test is all we have right now. And we can see how the integral test takes nice care of this series. So again, we don't have to worry about convergence because it diverges. So again, we did all the work in the proof. The proof took care of all the partial sums, so we don't have to write a partial sum here. We only have to make sure that the hypotheses are good, and then boom, do a what? An improper integral. And that's it. That's it. So this is what I was saying before. L'Hopital's rule we have used, okay, we have used outside of that section. Improper integrals we have used outside of that section because it comes up in an integral test. So again, maybe not the most important thing we do, but we do need to know how to negotiate them. So that's kind of like I've said many times with these kinds of problems, we have basically a topics type course where we go over here, we take this, we go over here, we take this, we put it together, and we get a solution. So that's really what makes the infinite series kind of fun, but maybe a little bit more challenging and different from what we've done in the past. So good. Now, I want to give you some nice results that you can put in the toolbox, kind of like the geometric and the divergence test and things like that. So the integral test is going to make our life a lot easier. So first, this is what Dr. Larson says is the P series. So we're going to make an observation. So first, observe. So we're not gonna make a big deal about this one because we're lazy. We just want to get to the punchline as fast as we can, even though sometimes that's not possible. So here we go. So we have 1 to infinity. Of course, that's flexible. It could be a 2 or 3. I'm going to write down the P integral. Now that's the P integral from the improper integral deal. We know that this converges when P is bigger than 1. This equals 1 over, we proved this. You can prove this. You know how to prove this for P bigger than 1. Okay, so you're thinking this is what we call the convergent P integral. So now you're thinking we'll just kind of work this backwards and create the P series. Therefore, this series n equals 1 to infinity of 1 over n to the P converges for P bigger than 1 by what? By what? The integral test, right? I know you're saying that in your minds, by the integral test. Boom, free, absolutely a freebie. Well, why? Clearly, we'll just say, note, f of x equals 1 over x to the P for P greater than 1 is positive, continuous, and decreasing on 1 to infinity. So we're thinking, okay, we got this very simple function. X is positive, so it's clearly positive here. 1 to infinity, it's positive. It's continuous because it's just a rational function. And actually a real function is just x to the minus p. So that's a power function, boom, continuous. And it's decreasing. Again, you can use the derivative or just say that the denominator is becoming infinite relative to the numerator and therefore must be decreasing, or do a quick test with the derivative. So what we see here is that this gives us an uncountably infinite number of what? Convergent infinite series. Because how many real numbers are bigger than one? You cannot count them. You cannot even list them. So the integral test gives us this theorem. This is what we call, this is what Dr. Larson calls theorem 9.11. So you're thinking, okay, so here's some examples. Now you can just write down an uncountably infinite number of convergent series. N equals 1 to infinity. We'll just be nice, n squared. We can actually sum that with Fourier coefficients. N equal 1 to infinity. Well, let's get creative. N to the 3/2. N equals 1 to infinity, etc. Just keep going forever. N to the 4, etc. Well, you can do n to the square root of 2. That's not the most interesting, but it will also converge downstairs. You see what I'm saying? Now we have all of these cases here that we can use as sources of comparison if we need them. You see that? So what's great about calculus is that we can get a few nice results and boom, 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 we get all this great stuff for free. So why did I do the proof of the integral test? Because of this, because that is a fundamental result. Why did I do the proof of the geometric series? Number one, it is a fundamental result, just like the fundamental theorem of calculus. If you do not know how to prove that theorem, you need to learn. That is an essential result in calculus, and any self-respecting STEM professional should know it. So, like I say, ladies and gentlemen, with this, we have extra for no cost. And then there's one more result that we again get for free. So here's what we call Roman numeral 1. What about the next one? Well, observe that back to the p integral. Observe 1 to infinity, and this doesn't even take anything. If I just let p equal 1, this clearly diverges, is a divergent p integral. Diverges. And so the theorem goes both ways, right? If and only if. Well, now let me, well, you know. So here, note f of x equals 1 over x. So equivalently, using the integral test, now we'll just write 1 over n. Remember, in the series, we take the f of x and a sub n is just f of n. So just like we have here, we have 1 over n equals 1 to infinity. Diverges. This is a famous divergent series. It's called the harmonic series, and that doesn't have anything to do with harmonics in physics. There are other reasons for this. So this is called the harmonic series. Give it a name. There are many ways to prove that this series diverges, but we get it for free with the integral test. Again, the integral test is robust. If the improper integral diverges, so does the corresponding infinite series. Okay, that is a remarkable result. And so now you're thinking, like I told you before, 1 over n clearly goes to 0. The generating sequence converges to 0, but that does not imply that the series converges. We've already learned that. If the series converges, then we know that the generating sequence must have limit 0. So that gives us the divergence test. So when you're doing infinite series and you write some reason, oh, well, 1 over n goes to 0, so the series converges, I probably should take off 20 points for that. You know why? Because that is in direct opposition of any logic that we have tried to learn with these objects. What I'm saying is this. This is a very sensitive test here, this P integral. And with the integral test, we get all of these convergent integrals or convergent series. Now, of course, as n gets negative, we're just getting like n squared, n cubed. Of course, that's going to just run off to infinity. That's no big deal. But this is one series that always confounds every student. They look at that 1 over n and say, well, that's got to converge. Here's the deal. 1 over n just does not get to 0 quickly enough. It does not get to 0 fast enough. You bump up the power to 2 or 3/2 or 1.1, and that is sufficient to give convergence. So that is a very delicate arithmetic component of the integral test. So here, this is like the second part, but this is what, again, you need to put on a note card and commit to memory. So you're thinking, later on, we're going to have what we call some comparison tests, which will be very easy to use because we have these. That is, we've got these convergent series here. We've got all these nice convergent series. That is these, and I've got examples here. And then we just pick on a value of P where we know this diverges and get the harmonic. So you might be wanting to prove, you want to compare two series and you want to prove convergence, so you'll pick one of these. You want to prove divergence, so you'll pick this one. So these will give you tools to compare series, which will be another technique that we use for determining convergence of positive term series. Now you're thinking, that's not the best, Professor Ron. That takes inequalities, and that doesn't seem very robust like this integral test. And you'd be exactly correct. They aren't. But one of the tests called the limit comparison test you'll actually like, because there will be limits like you did in pre-cal, where you basically have lots of intuition on your side. So again, look at the integral test and say, wow, look at all of this free stuff that we get. So again, put this on the note card. It will serve you very well. Now, I want to do some more examples with the integral test. But before I get to that, the other example is going to be utilizing the integral test to get a bound, but I promised you another interesting series. Look at this one. And then we'll go back to the integral test, which again, those are just improper integrals. Look at this particular one. This is an interesting example. N equals 2 to infinity of the natural log of 1 minus 1 over n squared. Now, you're thinking, okay, well, it's not geometric. 2, let's see, 1/4. Okay, 1. You're thinking, wait a second. I don't know, Professor Ron. That in this form, I don't want to integrate that. That would be kind of a nightmare. And you're thinking, well, maybe I could use some properties of the logarithm. So when you look at this, and here's how WebAssign phrases this problem. They put this problem in the integral test section, which is really unfair. And then they say, here's what they say: compute the sum. and you look at that and say, okay, well, maybe it falls into the telescoping category. And so what I would say when you have interesting things like this, I mean, when you think about the example here, this pretty much falls into a category pretty quickly. When you have the p integral, you see the category quickly. So I thought this was interesting, and I wanted to save it while we developed our skills a little bit. So it's kind of like looking at an integral. Okay, so what am I going to do? So what I would suggest, especially when you have logarithms, and you're thinking, you know, that might be a little bit difficult with the integral test. It's not geometric. You know, I'm going to keep my fingers crossed and say probably telescoping. So my first piece of advice would be to use identities of the logarithm. So this is a unique problem. So we have the natural log, and then of course we have the n squared. We can get a common denominator. And I wanted to tell you that I'm fairly honored. One of my colleagues found out that a lot of my Cal 2 material is on these websites where you have Homework Chegg and Course Hero and stuff. And I know that's going to happen. It invariably happens. But he was saying that the material from the North Campus is heralded as being some of the best, and I'm not surprised. So if other students from other schools benefit from my notes on mathematics, then that's fine. I don't really care. I just want you to learn it. But I have some wonderful colleagues, and they know that my love for math transcends basically their love for math. But they respect the fact that I am honest with my students and that I'm rigorous. And so good. Share the word that if you want to really learn some math, come to the North Campus and be prepared to put in some time, but be prepared to learn. So I thought that was nifty. There are all kinds of things out there these days that weren't around in the dark ages when Professor Ron was a student at Carolina, long before you all were thought of. Okay, so now we've got the log of a quotient, right? So let's do that. Natural log of n squared minus 1 minus natural log of n squared. Okay, so now, of course, we can factor this. When I looked at this, I thought, what's the professor doing? And then, of course, I looked back in my notes and I had written this up one way. And I thought, well, let me think of it a different way. So we have natural log of n plus 1 times n minus 1. So that's a product minus 2 times the natural log of n, again, which is the power rule. So let's keep going. N equals 2 to infinity. And so we'll have the natural log of n plus 1 plus the natural log of n minus 1. And then we've got 2 copies of negative log n. And again, this was what I was talking to you before. You can write this up and write out a bunch of terms and all, but I'm trying to get away from that, even though I think it's comfortable. And when you look at notes, it's like it's easier for students to follow. But sometimes that's more effort than it's worth. So here's what I want to notice here. And this is what I thought might be good comparing this to the geometric series proof. If you look here, these 2 arguments are separated by 1, and these 2 arguments are separated by 1. So let's group them together. And they have opposite signs. So you see, this is indeed telescoping. So what I'm going to do is pair these, this one with this, and this one with this. So the natural log of n plus 1 minus the natural log of n plus, here we've got the natural log of n minus 1 minus the natural log of n. Now, just like before, you can just start substituting numbers and write out plenty of terms and show that pretty much everything absorbs. And what does that leave you with? You know, just like I was talking about before. And there's certainly merit to doing that. But in some cases, it's more work than we need to do. Let's just notice a couple of things. Notice here, this, when n is equal to 2, this will never be 2, okay? This is one more than this. So when n is equal to 2, this term here will never be annihilated. But when n is equal to 3, again, excuse me, n is equal to 3, then we have the 3 here, and then this is a 2, and then as we keep moving, what we're going to see is that this will start knocking these off. That is, as we build, these will always eventually absorb each other, but the negative log of 2 will never be absorbed. Now go over here. If we look here, this n minus 1 here will be absorbed by the n, the log n term, but this will never be n minus 1. This will always be greater by 1. So when n is equal to 2, we get a log 1. That's 0, but it's not going to be absorbed in the classical sense. So what we see as we start moving up, this gets larger, and then that will be killed by the previous set of parentheses. Again, they're just displaced by 1. So these absorb. So what you end up with is n equal 2, so you get what? Negative ln of 2, and then plus ln of 1. This is when n equals 2. And the rest absorb. And so that's 0, so you get negative log 2. That's the quick way to do it, by noticing that these will always cancel or absorb each other. I use cancel, oh my goodness, don't do that. They'll always absorb each other. But we notice that because of the disposition of the arguments, there'll be 2 terms that will not go away. And this is infinite, ladies and gentlemen. So as we start moving along infinitely, it never stops. Like when we did that partial sum before, we had stuff at the end that didn't go away, but it also went to 0. So we could have ignored it. So the idea here is that in the infinite sum, these terms will always absorb each other, offset by 1. But the negative log 2 here and the positive log 1 don't get absorbed, but that's 0. So the sum is the negative natural log of 2. That's the quick way to do it, by analyzing the telescoping nature of this series. This is a difficult problem, and I doubt that many students would understand how to do it or ever get it right, even if you had done the whole chapter on infinite series, unless someone had explained it to you. So the thing is sometimes the problems basically just result in something very, very simple. And this is what I want you to think about. Go back in my notes, in the notes on Blackboard, and you'll see that I've written this out with all the substitutions. And I work out a little nice pattern, and I'm thinking, okay, yeah, that I think I might have it over here. Let me check. Oh, I certainly do. I do. Let me show it to you. See if I've got it right here. Yeah. What I did is I noticed a pattern here. And then on the second page, I simply just wrote out the terms and showed how we did all the telescoping and all of this. That takes forever. And you get the same answer. Thinking of writing this as a partial sum and then taking the limit. So doing it in a very elegant mathematical way, it works out fine. And it's actually kind of beautiful the way it works. But look at all of that work. So I thought, well, sure, I can show that to my students and they can work on that. Or we can simply analyze it from a telescoping vantage point and get to the punchline a lot faster. Now, of course, I'm all for rigor, but when you look at this and you analyze it the way I have, then there's no need to move any farther than this, and not even a need to look at the partial sum, because again, the partial sum just simply gives you a term that goes to zero. So the beauty here is that you can reanalyze and actually observe the telescoping nature of this in a more, I guess, clever way to get to the punchline. So I want you to compare the two results. Do this and then compare it to what I have in the notes on Blackboard, and you'll see that you probably will prefer this. But again, this is hard to see. And I thought about this, and I've thought about this many times when I teach calculus too. We can always look at these telescoping problems just like we do the proof of the geometric series. Now, the thing is that because these are offset, you have to look at the fact, again, analyze the case n equal 2, and then hereafter, everything goes away. And since it's infinite, everything absorbs, again, offset by 1, but everything gets taken care of. So look at that and do the comparison. I think that's a very, very interesting problem. Now, the next result I want to talk about has to do with remainders. That is, can we use the integral test idea to actually approximate the sum of a positive term series within certain decimals? And the answer is yes. So here's what we want to do. So for instance, we can use the ideas of the integral test, to approximate positive term series. That is, as long as we can do the integral. I mean, there's always a catch. Positive term series. So we're going to use the same idea that we had before. So for instance, here's the idea. Suppose, and we're going to use that same partition type idea that we had before. Suppose S sub n, and I'll use, Dr. Larson uses uppercase N just to kind of give it a little bit more distinction. S sub n we're going to use to approximate the series. So we're going to say this. So again, I'm going to go ahead and write this with the K. So remember, let me just write over here. A sub n will equal f of n. That's how we did the integral test. Remember that? So I'm going to use that notation. So we're going to go from k equal 1 to n of f of k. Note that the sum, the infinite sum, we can just denote as just a plain S. We can write this way. And I'll use the same indexing just for clarity. So that would be the infinite sum. So if we have the convergence setup, then we're saying, okay, well, what does this do with remainder, so to speak? So this implies, again, these are positive term series. So S minus the partition is a positive number because these are positive term series, or minus the nth partial sum. So we'll have 0. So what's the remainder? Well, it's actually the difference between the actual sum and the partial sum. And since it's positive term series, we know that this is non-negative, and certainly any case would be positive. So now we're thinking, okay, these are all lined up like we did with the geometric series test. So let's take the difference, and we've got the same generating sequence, so we can get the following. So we're going to subtract this from this, and this will leave behind k equal n plus 1 to infinity. But now we can think of the fact that we're going to use these in our Riemann approximation as a sum. And so now we're thinking, we start here and we start making our rectangles, and these would be a lower bound to the actual improper integral, just like we did before. So if we go from n to infinity of f of x dx, this is an upper bound using the same criterion that we did in the proof. So again, it's kind of like you think you've got this right endpoint, and you construct the rectangle on that, and that's going to be the lower sum. And so the integral, which is exact, is going to be greater than that. And that's going to start at n and move on out to infinity. So this is using the same construction that we used before, but in a way that gives us a nice approximation. Therefore, we can use this as an approximation of the actual remainder. And so we can compare this to some decimal approximation that you want and figure out how many terms we need in the partial sum. So we have this R sub n, which is non-negative, will always be bounded above by this integral. So again, this is just using the partition and the lower sum relative to the exact value of the improper integral. So what's beautiful about this is that this is not too terribly hard to compute when you've got powers of x, you know, like 1 over x to the 4th or something like that, or 1 over x to the 5th. Those are easy to compute and doable. So this is what makes the integral test even better. So all of these nice convergent integrals that we have from the integral test, we can now say you're doing an engineering project or a physics example, and you're thinking, well, I need some terms of this positive term series, but I only need this much accuracy. So how many do I need? Well, you can pull out this result and compute what you need. So here's an example that we want to do with this. So let's do an example using this. So we've got our nice result here, which we'll use. So here's an example from the WebAssign, which makes a good test question. Example. So compute the smallest n. This is the notation for WebAssign. That's why I use the n. Dr. Larson uses this, such that the remainder is less than or equal to 1 over 1,000 for the convergent series. And here it is. Here's one that's convergent. And so we can use, again, we'll compare the 1/1000 to this because we can compute this. This is an unknown, but this is an upper bound, and it's a good upper bound, and it's going to give us, we're going to get even better than 1/1000 because this is an upper bound of this. So we're getting even better than the problem, basically, but better is always good. Better is always good. It's like, can I give you more money? Sure, more money is always good. We won't have a problem with that. It's kind of funny. Common sense is useful, but common sense, as you well know, is uncommon. So we'll do our best. So now what we're going to do is look at the integral. So that is, this implies analyze. In this case, the integral n to infinity 1/x to the 5th dx. So we want to analyze, and then we want to compare this to 1/1000. So that's what we need to do. So let's do this. So n to infinity, and we'll just write it as x to the -5th because we like the nature of this because it's easy to work with. So this will give us the limit as b approaches infinity. So this will be n to b x to the -5th dx. So again, like I said before, we'll probably end up doing more improper integrals where the upper limit is infinite as opposed to infinite discontinuities in the integrand. But that's okay. This just comes up more. And so we get the limit as b approaches infinity. And so add 1 divided by the new power. So that's going to be what? X to the -4th divided by -4. From n to b. So we get the limit as b approaches infinity. I like this material. I think you'll like it too. It's fun and makes for good conversation about math. Now, the -1/4 we can just extract. And we can just write this as 1/x to the 4th. So we get -1/4 limit b approaches infinity. So we get 1/b to the 4th minus 1/n to the 4th. So we know this integral is in good stead. We know it converges because we have a convergent series. So we don't have to worry about that. All of that is taken care of by the integral test. And so of course, as b tends to infinity, this is just 0. So we get -1/4, 0 minus 1/n to the 4th. So this equals, the negatives absorb. So we have 1/4 into the 4th. And we want this to be less than or equal to 1/1000. So we just want the first integer, positive integer, such that this is true. That's all we need to do. And we can do this. These numbers are good, but like I say, ladies and gentlemen, the integral test gives us this really nice upper bound for the remainder here. And we'll use this with the alternating series test. So one nice thing about this is easy to remember. This is a very simple integral to remember. So it's something you can carry with you long after this class is over. Again, this is easy to remember. So now we can reciprocate. So we have 4 into the 4th is greater than or equal to 1,000. So we can divide by 4, so that'll give us 250, right? So now that we know that that's close to 256, which is a perfect 4th. but we'll just say here, n is greater than or equal to, and so we got what, 25 times 10, so that's 5 cubed times 2, so this is 5 cubed times 2, and this is the next closest value, perfect fourth, is 256, so this implies choose n at least 4. So when you look at this problem, again, that's not a perfect fourth, but we just observed that 4 to the fourth is 256, which is greater than 250. So that's what I use there. So again, it's important to be rigorous. It's important to work things out. I think what I want to impress upon you is that as you learn techniques, you can do more or less. You can say, well, I can see that this is continuous. I can see that this is the case. I like to give you techniques that allow you to move to the next level. Now, of course, if there's a question that says, well, do this more rigorously, use the partial sum and show that this is telescoping. As long as you know what you're doing, you can write the mathematics and then it's clear. Just maybe a little line like we would say, these arguments are separated by 1, and the sum will telescope as n tends to infinity. So how does this problem differ? Well, in this particular case, we don't have telescoping. We just have the computation of a straightforward improper integral. But it's a little bit different because we have the unknown lower limit, which is a finite number. And so we work this out. There's no efficiency rating here. We have to do what we have to do. So again, it is important as a STEM professional to be able to know how certain analysis can move you forward that will cut out some work that may or may not be necessary. For instance, as we work this problem, we get to this point and we clearly know that this converges to 0. We don't even really say anything about it. We're just like, well, that's clearly 0, and we move the problem forward. So the idea is to analyze what you need to do and make good choices. And I know that most of you do that, but make the choices based on your ability to analyze, not using fancy equipment that and computer programs that just make you less good at what you do. It's much more honorable to work the problem out and find an error because it was inconsistent in another part of the problem. That's how you work the mathematics. That's how I do it. Even as a graduate student at Texas A&M, teaching the kids Maple, I told you this before, they were always mad at me. I said, don't get mad at me. The engineering school wants you to learn this. And they want us to teach you how to do it, but they could never use it on the test. I said, well, those are the rules. Like I say, they would bring a piece of paper and a pencil to the test. That was it. Drove those poor kids crazy, but that's fine. You live and learn and figure out what you need to do. Now, with the other examples on the integral test, if you see a quick way to do a problem and you can compare it to something else that we've already done, then that's fine, work that. You use whatever tools you need, practice the integral test, but we kind of washed ourselves with the integral test because it's given us so many neat things. Now, I just want to give you a preview of where we're headed next. These will be the comparison test, and I got a little bit, so we'll talk about the comparison test and the alternating series next week. Now you're going to have your next test at the end of the week. I don't know if I'm going to have any lecture time on Wednesday. If I do, it'll just be very short, but I'll still give you the luxury of the 3-day window. Again, that is my decision to give you the flexibility with the testing date, and I think it's a good one. I do ask a lot of you. I do the same for my other classes, though they don't always see the value in it because they're not as mature as you are. You're older students in the sense that you're older mathematically. You've taken more mathematics, and so you have different ways of looking at things. But just keep that in mind as you prepare for the next week. What I wanted to do is just give you an idea of where we're headed with the next set of theorems. And these are in your notes for on Blackboard. And what I wanted to do is that now that just to kind of give you an idea of what we're actually going to work with. These tests are for positive term series, and they're not as elegant as the geometric series test, or even telescoping, or the famous integral test, which again has been bountiful when it comes to results in mathematics for series. And I've done this in red here, and I've written positive term series. With the geometric, R can be negative. Okay, so the terms don't always have to be positive, but at least with the integral test, we've seen positive. And now we're gonna still focus on that. When we get to the ratio test and the alternating series test, then we'll be a little bit more flexible. But I just wanna go ahead and give you a brief introduction to what we call the direct comparison test here. And for some reason, when I wrote these notes, they were just, I just must have been in the neatness mode because these are beautiful. You know, the thing about mathematics is that you have to be able to write it, and so you practice when you do your math, make everything look good, and use your eraser bit. These are good. Buy these on Amazon. You can get a big old package and usually a reasonable price. I think I keep them in business. So what we're going to do here is look at a very simple test that can actually use some of the convergent series from the integral test in that famous divergent series, the 1 over n bit, the harmonic. And it goes like this. This is called the direct comparison test. And we've got two sequences. Again, remember, I just used the subscript notation for the sequence, and they're both positive term. So again, this is very important. And we consider sequences AN and BN such that this is true. That is, when you want to compare two series, you must establish an inequality. Again, that's why students say, pass on this. I don't want to do all of this, and it takes too much time, but this is a good test. So we establish an inequality based on the generating sequences, A sub n and B sub n, and say we have this. That is, we know that these are positive, so that's a freebie. And then we have this inequality here. So what's going to happen is you will have one series, and you will either have B sub n or A sub n, depending on what you want to do. That's where the trickiness comes in here. So if we have this inequality right here, then we're thinking, okay, what can we do to show convergence? That is, can we show that A sub n is convergent? Well, if B sub n is a convergent series, that is, if we use this generating sequence here to generate this infinite series, and it's actually convergent, and we have this inequality with the generating sequences, then the sequence based on A sub n converges. So that is useful. And then you're thinking, well, what about divergence? Well, if we still have this inequality, which we do, and we can show that the infinite series based on this generating sequence diverges, and of course, this is a lower bound for this, there's really no hope for the series determined by the B sub n. So again, this would diverge. So you're thinking, if you can come up with a relatively good inequality, this is really not so bad to do. Now, what I would like you to do, just to kind of give you one leg up, go ahead and look through the notes. We're going to cover these. Notice these are going to use the monotone convergence theorem. But I just wanted to give you an idea of where we're headed. And then the very next one is going to be the limit comparison test, which will be of a similar nature. Okay, now what's more popular? Well, the students like the limit comparison test because they like taking limits and they don't require all of the fancy inequalities. So we'll look at both of these, and as you have time during the week, once you finish up your homework and quizzes, go ahead and look through this in the notes and see what you think about it. And we'll spend some time with this next week. So basically, for this next test, we will stop with the material on the integral test. Clearly, none of this will be covered. This is just a brief, tiny little introduction to what we're going to do next class. So make sure you go ahead and get your homework completed. And then, of course, I've moved everything kind of more into the week to give you a little bit more time. I think maybe that's a little bit better for everybody. I just want to make sure you stay on schedule, but moving the homework into the middle of the week and then the quiz maybe gives you a little bit more flexibility. And so I hope that's helping out. But I appreciate your attendance today. Ladies and gentlemen, be sure that you take time for the class as you've been doing. As we continue through the class, it's really not going to get much harder, but it's really not going to ease up much. And even when we get to the polar coordinates and the polar integrals and stuff like that, students find that to be tricky because it's using a lot of trigonometry. So just be sure to carve out plenty of time to work on this class and keep yourself sane and stay healthy. Don't get the congestion that Professor Ron has, but take care of yourself. And I appreciate your attendance today. And if I see you at conference hours, fine. If not, we'll see you soon. Take care, everybody.